today we will start the second chapter on in this course, and will now be, because we will be dealing with classical systems where quantum corrections are not required. Okay. So, this is the chapter that we will take on, and the subject of classical statistical mechanics is beautiful in the sense that we are not really focused about exact time evolution of trajectory of particles in a system. Okay. So, if you are looking at let us say the particles of the gas in this room, I would be interested in understanding what are the thermodynamic states accessible to this system. Okay. By thermodynamic states I am saying the macro states available to the system, meaning for example the values of number of particles, volume of the room and total energy of the room. Okay. So, this would be example of a macro state. You could also say that I am interested in number of particles, pressure in the room and the temperature of the room. Okay. So, we are dealing with systems at equilibrium, and we are asking questions about states of the system, which can be represented by the combinations of these variables that I have written down. So, these states are called as macro states. Okay. And a macro state by itself is basically characterization of system with very small number of variables. As you can see, I have taken in each macro state I have taken only 3 variables, but a given macro state, for example NVE, which means if I take this room at a given value of N, V and E, then you can classify the system. You can say that this particular macro state consists of several microstates, each different from the other in terms of the location of the particles and their momenta, So, I can take one macro state and take the system in several different so these are basically microstates. Okay. So, this is like the specific arrangement of particles and momenta in the phase space. Now, by phase space I mean the system, the coordinate system of their degrees of freedom in coordinates and degrees of freedom in momentum coordinates. So, the phase space here corresponds to three n momentum degrees of freedom for an n particle system plus 3n position degrees of freedom. So, this is basically a 6n dimensional space. Okay. this is coming from momentum and this is coming from position, and in this phase space I can represent a microstate by a single point. So, each of these mu i's that I have specified can be represented as a single point in the 6n dimensional space. So, it is hard to visualize this space, but you can think of 6n orthogonal axes. So, one of them could be the px x component of momentum of the first particle, then you can take another coordinate as py of the first particle, and in this way you have taken you can take one more here. So, you can take the 3n degrees of freedom and now you can also take coordinates. So, here a microstate here could be just one point, is just one point here. So, I will say this is, let us say, microstate mu 1. Well, this only means that if I project this microstate on any of the axes, let us say if I project it on the axis px1, then I will get the x component of the first particle. If I project it on the axis py, then I will get the momentum y component of momentum of the first particle, and if I project it on q and z, I will get the z component of the nth particle in the system. So, in the 6n dimensional phase space, the system is actually just a single point. And the evolution of system through these microstates, the system can go from microstate mu 1 to microstate mu 2 all the way to mu n, and these large number of microstates, clearly n is very large here, n is not the number of particles. I should use a different symbol here, the small n, I will use a small n because capital N is reserved for number of particles. So, I will use mu n. So, clearly number of microstates are large, and they seem to sort of occupy these the phase space in such a way that the projection of each microstate on the corresponding axis gives the coordinate of momenta or the position of a particular particle where you are projecting the phase space point. So, where you are projecting the microstate on. So, basically what is being said here is that you do not really, it is it is not required to time evolve the coordinates as you would do in classical mechanics. It is not required. Okay, that means that in classical mechanics you would take a Hamiltonian, which is basically a function of your position and momentum, and you would normally take the time evolution of the position and momentum through the Hamiltonian. So, the equation of motions that you start with basically minus P I dot as del H over del Q I and Q I dot as del H over del P I. So, you do not in statistical mechanics you do not do a time evolution of your coordinates exactly. So, what you do basically in any equilibrium system is basically we study the distribution functions. I will describe what these distribution functions are, and for each of the equilibrium systems that I have discussed or I have described not described mentioned in the at the beginning of this lecture, such as NVE systems at constant NVN energy. This system is called as a microcanonical ensemble. We will describe I will describe these ensembles in detail, or when you specify the number of particles, pressure and temperature, which we call as the canonical ensemble. So, I will call this as a microcanonical ensemble. This is a canonical ensemble, or you could take Gibbs canonical ensemble. So, instead of studying the exact Hamiltonian evolution, or the evolution of the trajectory of particles, we will be concerned about the stationary properties of these systems. Okay, so by that I mean that I will not be concerned about single particles anymore, where the amount of information available is huge, but the problem also becomes intractable. Instead, we will go to the information of distributions. Okay. So, with that in mind, I will take the first ensemble, okay, which is a microcanonical ensemble. And the prototype system for each of these ensemble will be gas in a box. Okay. So, I am going to take for example an ideal gas, okay, in this box, and I am going to take this box with n particles, volume V and total energy E. Okay. So, this is going to be my microcanonical ensemble, and as I said that NVE represents a macro state here. So, you can specify number of particles to be of the order of 10 to the power 23. You can specify the volume to be maybe some 100 liters, okay, and you can specify some energy to be some joules, okay, so x joules. And so, once you have specified this with the values of number of particles, volume of the room and the total number of total amount of energy in this room, you are now basically in position to do some statistical mechanics on this system. Okay. So, by that I mean this is a system where a macro state, okay, is specified by the condition that any microstate will have a Hamiltonian that is nothing but the E that is specified. Okay. So, you have specified the energy to be E, and the system could be in any microstate. Okay. By microstate I mean the exact position of the coordinates of the particles, okay, the momentum coordinates and the position coordinates, and as long as the Hamiltonian of the system is E, which is the energy specified, then this probability of finding the system in that microstate, okay, corresponding to a macrostate M, would be nothing but 1 upon the total number of microstates that the system has access to, and this will be a function of E and V. So, if I increase the number of particles, or if I increase the volume, then the number of accessible states will also increase. Okay. And so, this is as long as your Hamiltonian is equal to the specified energy. And I know the moment we pick up a microstate where the Hamiltonian is not equal to E, then we will say that this is 0. So, the microstate has 0 probability if the energy corresponding to that microstate is nothing but E. Okay. So, so omega here corresponds to a number of microstates accessible to the system, and the fact that I have taken each microstate to have a probability of 1 by mu, this essentially means that I am going to write it here. The fact that I have taken the probability of any microstate corresponding to a macrostate M as 1 upon omega if h mu is E, this means that I am assuming equal a priori distribution, or equal a priori probability distribution. So, the meaning is if your macrostate has omega microstates, then each microstate has an equal probability for in that macrostate. Okay. So, with that consideration, you can always write down the Boltzmann hypothesis for entropy as kb ln omega. Okay. So, this equal a priori probability distribution allows me to invoke the Boltzmann's definition for entropy, which is nothing but a statement that the entropy is it's an additive extensive quantity, and the calculation of entropy is logarithmically related to the number of states accessible to the system. Okay. So, armed with this important rule, we can look at some cases, interesting cases. We can actually revisit some laws of thermodynamics. In fact, we can derive statistically laws of thermodynamics in the context of microcanonical ensemble. So, we are going to stick to microcanonical ensemble, and give some discussion on laws of thermodynamics. So, the first law that I would discuss is the zeroth law of thermodynamics. Okay. Now, I would not state the law straight away. In fact, I will present a small experiment, and the zeroth law of thermodynamics will appear naturally at the end of it. So, let me just take two systems at equilibrium. Okay, so, these are two systems that are let us call the systems as A and system B. And let us say that they are at equilibrium. Both thermal and mechanical equilibrium. Now, the meaning of this is that these systems are thermally isolated, which means there is no exchange of heat with the surrounding. So, there is absolutely no exchange of heat with the surrounding, and you have fixed walls that cannot move. So, there is absolutely no way in which energy can leak out of the system. And the walls are fixed, so the volume cannot change. So, they are thermally and mechanically isolated, and the systems have an energy content. Let us say the energy content of this system is E A and the internal energy of the system is E B. Okay. So, the systems are in thermal and mechanical equilibrium, and if I ask you what is the entropy of the system, so you can individually say that the entropy of my first system would be Kb ln omega A, where omega is the number of states in which our system A can exist, and the entropy of the system will be Kb ln omega B. So, where omega A and omega B are the number of states in which systems A and B can exist. Okay. Now, let us connect these systems. So, now I am going to connect these systems. Okay. So, let me so this is my system B and this is my system A. I have connected these two systems in such a way that the system A and B can exchange energy. Okay, but they are shielded from the surroundings. So, A and B will not take or give any energy to the surroundings, they can exchange energy internally, okay. They can exchange energy between themselves, but they are still isolated both mechanically and thermally from the surroundings, okay. So, A and B can exchange energy now, okay. Only energy, the walls are all fixed. So, there is no volume exchange between the A and B. Now, what happens to the, what can you tell about the joint entropy of the system? Okay. So, let us say immediately after you have connected the systems, the entropy of the joint system is S A, a function of E A, plus S B, a function of E B. This is the total entropy. But wait, the system is the system is redistributing energy. So, you wait for some time, wait to equilibrate. So, you come back after some time and now you see that the total entropy keep in mind that the total system is isolated, which means our energy initially was E A plus E B, okay. It is still E A plus E B, and I have called it as the big E, okay. That is my energy. So, I am going to underline this, that my total energy has always been E A plus E B, okay. So, what has happened is, after waiting for a long amount of time, I see that the energy of my system A has become E A star and the energy of my system B has become E B star. And if I call this as the equilibrium state of the joint system, I can write down the final entropy, which is S, the total entropy of the joint system, and the joint system has energy E, as the entropy of system A, but which is now sitting at energy E star, plus entropy of system B, which is now sitting at energy E B star. And this is actually a state of maximum entropy. We can prove that this is a state of maximum entropy, because if the systems had different energies and they exchanged energy between them after bringing them into contact, then there is no way this system will go back to its initial configuration on its own or spontaneously, which means this redistribution of energy was irreversible. And when you say the energy was irreversible, this redistribution was irreversible, the entropy of the system has definitely increased, okay. And we can find this out. So, what we really mean here is if you look at the change in entropy, which is delta S, okay. So, you can think of you can find out the change in entropy from so I am going to write down the question, that what is the condition for equilibrium. Okay. So, the condition for equilibrium is nothing but a certain state where these entropies of each subsystems A and B have maximized. Okay. So, for that we must allow for establishment of identical temperatures on both sides, and that is a condition that will derive, okay, as a consequence of entropy maximization. So, you could basically say that the change in entropy, okay, of the system A would be ds A over dE A at constant volume, okay, and you can think of change in entropy of system B as ds A, this would be total entropy. So, this would be okay, and the overall change in entropy would be nothing but delta S A plus delta S B, which is nothing but delta S A upon delta A E A plus this is the overall change in entropy. And now I am just going to recall the fact that the total energy of the system is constant. So, I will write down E as E A plus E B, okay, which is of course also equal to E A star plus E B star, the sum of final energies, but that is not required. Okay, then that means I can write down my delta E, which is 0, which is equal to delta E A plus delta E B. It simply says that delta E A is equal to minus delta E B. Okay. So, if you substitute it upstairs, what you see here is that the delta S comes out to be delta S A over delta E A into delta E A at constant value of E A, okay, plus delta S B over delta E B at constant value of V B, and I am substituting delta E B as minus delta E A, okay. And if you take delta E A constant, now you are looking at a condition for equilibrium here. Like I said before, if the evolution of your two systems after connection was such that there was an irreversible change, okay, some energy went from a hot system to a cold system. Now, this is an irreversible change. You cannot after the two systems have equilibrated, you can't bring the energy back you can't recover the initial configuration. So, there is some amount of information that is lost, which is said as the change being irreversible. Now, when the change was irreversible, you will definitely expect a positive change in the entropy, it will be greater than 0. But we are chasing a condition for equilibrium, which means if you are at equilibrium, then there will not be any change in entropy. Okay, any change of energy from any passage of energy from body A to B is reversible, because you are at equilibrium. And if that is the case, then for any arbitrary energy change, to make delta S 0, I must demand that my prefactor here is 0. Okay. Only then my delta S will be 0. So, if equilibrium is achieved, and by equilibrium I mean thermal equilibrium, then I have to demand that the prefactor is 0. The prefactor is simply delta S over delta E A at a constant volume equals to, if the bracket is 0, which means these two values are equal. This is the condition for equilibrium, and I can now define empirically the empirical temperature as 1 upon T. So, if I define ds over dE as 1 upon T, then this quantity ds over dA at constant value of ds over dEA at constant value of volume of system A is nothing but 1 over inverse temperature for the system A. So, I will say this is A comma B, similar this is A comma B, this is A comma B. Okay. So, the condition for equilibrium is simply equivalence of the two temperatures. So, remember how we derived this condition for equilibrium. We just computed the change in entropy for redistribution of energy between two systems. Now, as long as we are away from equilibrium, this change in entropy will be non-zero, which means your temperatures are not the same. The moment you reach equilibrium, which would be, let us say, after an hour or after 2 hours or after 10 hours, whatever be the case, when you come back and now when you compute change in entropy, you will see that there is absolutely no change, because any energy that is exchanged across these two systems at equilibrium is basically a reversible change or reversible process, and when that happens you take the entropy change to be 0. Okay. And this would be the condition of thermodynamic equilibrium between the systems A and B. So, this is like the 0th law of thermodynamics, which essentially says that the two systems will continue to exchange energy until the temperatures become equal. Okay. So, for example, you connect them, wait for half a minute and ask yourself a question, has the equilibrium been achieved? Well, you will see, are the two temperatures same? If the two temperatures are not same, you will wait longer, because when the temperatures are not same, any energy distribution, any energy change that has happened between the two is not reversible. Okay, it is irreversible, and this irreversible exchange of energy will continue to happen until the two temperatures are same. That is the condition for equilibrium. we can proceed from here and derive the first law as well. So, you can derive the first law. Which is essentially nothing but I would say it is a bookkeeping of energy. So, you simply associate the first law of thermodynamics as a law of conservation of energy. Or bookkeeping of energy. You simply account for each mode of energy injection and work done, and the first law of thermodynamics is nothing but a statement of energy conservation. So, we shall see what that means. So, suppose you take a system at equilibrium. So, consider a system at equilibrium. Okay. So, this is a system having some energy E and some volume, and some number of particles, some volume and energy E, and the system is at equilibrium. Okay. So, now what we do is we allow. So, at this stage let us say the entropy of the system was a function of E and V. Okay, we are keeping n constant. So, we can drop n, and what I am doing is I am allowing the system to expand a little reversibly. So, there is some expansion of the system that I call as that I will address as delta V. Okay. So, some reversible work, and this reversible work is basically because it is an inexact differential. I am using a this horizontal bar here means that this work cannot be traced, it is basically path dependent. Okay. It is not an exact differential, and so this is this highlights this is highlighted by this strike off, and I call it as minus p into delta V. Now, the reason why I have taken a minus sign here is that any work done by the system will lead to reduction in its internal energy. So, if you take a system and allow it to expand, there is a delta V which is positive. So, P delta V is positive, but minus P delta V will be negative. So, its internal energy will be reduced because the gas has done some work. So, it is now sitting at a lower internal energy. It did work on account of its internal energy. So, we are taking the convention as minus P delta V. That explains the minus sign. Now, what has happened after this small expansion is that n has remained the same, but both V and E have changed. Okay. So, my system is now sitting at n V plus delta V and energy E minus P dV. Okay. Fine. So, let us compute the change in energy, change in entropy. So, this change in entropy due to this reversible work that we did on the on our system is basically delta S, okay. But I want to know what is this delta S, a function of E and V. We can compute this by a simple first order Taylor expansion. So, we can compute the entropy, the final entropy by a simple Taylor expansion. We say that okay, energy after the work is equal to the energy before we did the work plus delta S over delta E at constant value of V into dE plus delta S over delta V at constant value of E into delta V. This is a first order expansion of entropy, okay, around E and V. We have expanded around E and V, okay. As you can see that these derivatives are taken at E and V here. So, this is a first order expansion around energy E and volume V. Let us call this as equation 1. Now, you recall that the system is thermally isolated, okay. So, I will say that my delta Q is 0, okay. And so, the only change in energy that can happen is due to the work that has been done on the system, okay, which is basically minus P dV. Okay, the energy of the system can only change due to the work done on the system because the heat given to the system is 0, it is thermally isolated. So, in equation 1 I can substitute this this thing, and I can take I can write down this equation 1 as E S of E minus E at the final energy values and the volume value, and I will take S of at initial values of energy and volume on the left hand side. On the right hand side I will write as ds over dE at constant volume into minus of P delta V plus ds over dV constant value of energy into dV, fine, and call the left hand side as the change in the entropy, okay. And the right hand side you can take delta V outside common and call this as delta S over delta E at constant volume into minus P plus delta S over delta V at constant energy into delta V, okay. And now what we have learned from the first law discussion, that the thermodynamic definition of temperature is del S over del E, okay, at constant volume. So, what we will do is we will substitute this in this expression. So, our delta S becomes minus P over T, okay, plus del S no, in fact what I will do here is yeah. Okay. Now, this is a variation in the entropy that is done very slowly, so that I am always at equilibrium, because if you remember this variation is due to reversible work, which means I am always at equilibrium. So, delta S must be 0. Why? If delta S is not 0, then basically I have lost some information permanently, and that is the indication that the process is not reversible. Any loss of information is basically a consequence of an irreversible process. You can't recover it. So, that would be associated with a positive change in entropy, and if I am claiming that the process is reversible to begin with, then this delta S must be 0, okay, no information is lost. That means for any arbitrary delta V that I take, okay, this variation in volume is arbitrary. I could have taken change in volume as per my liking, but any arbitrary volume displacement that I take such that the work done is reversible, then that should lead to 0 entropy change, and that is only possible if the prefactor here is 0, because delta V is not 0, it is arbitrary. The product of two numbers is always 0, one of them is arbitrary. Well, you will say that the second number has to be 0, okay, because I can take delta V to be non-zero. So, this is only possible, the product will go to 0 only if the prefactor here, which is what I have written in the parenthesis, is 0. So, I will write down P over T is equal to del S over del V at constant energy. So, now you can compare equation 2 and equation 1 and rewrite equation 1. Okay. So, what I will do here is basically take the entropy on the right hand side and left hand side, okay, and write down equation 1 again. So, I am going to just yeah. So, basically what I am going to do is yeah. I am just going to write down equation 1 again. So, just using equation 2, I can say that delta S is basically, we can write down ds over d as 1 upon t, and if you look at the third term here is ds over dv at constant energy, which is equal to p by t from equation 2 into the variational volume V. Okay. So, now including all variations, which means you are no longer using these infinitesimal derivatives. If you include all variations, I can write down this this law as ds equals to dE over T plus P dV over T. In other words, I can write TdS, which is the heat given to the system, as a change in internal energy plus work done by the system. So, this is basically your first law of thermodynamics, which if you see is nothing but an energy conservation statement, that if you give an amount of energy to the system, which is TdS, it will only increase the energy of the system by an amount dE, plus if you allow the system to expand, the work done would be P dV. Okay. So, that is the statement of the first law, and with this we are now in a position to look at the second law of thermodynamics, which is basically a statement of so I am now going to discuss the second law of thermodynamics, which basically gives you the arrow of time. Now, what is meant by the arrow of time? It simply means that, look, so far we have taken two systems and we have connected them, and we asked the question, what is the condition of equilibrium? So, the condition of equilibrium is wait long enough such that the temperatures become the same, fine, but we do not have any idea as to what is the direction of flow of heat, net direction of flow of heat from one body to the other, which is basically saying in which direction the time will propagate. Okay. So, in other sense we are basically asking a question, what would be the direction of heat flow okay. So, what is the direction of heat flow? In our problem of heat conduction. So, we can give this direction of heat flow from the second law. So, you can basically say that the total entropy which is given as S, and that is nothing but S A function of E A plus S B a function of E B, which is basically soon after I will just call it I just call as S A plus S B and give the independent variables very shortly. Okay. So, I am going to write down the situation right. So, I will write down right after connection and at equilibrium. So, at equilibrium I know that the entropy would be S of A at E A star plus S of B E B star, and right after connection was S of A E A plus S of B E B, and this entropy is definitely larger than the entropy to begin with. Okay. So, that is the entire concept of irreversible change. So, the initial entropy is definitely lesser than the final entropy because you have lost some information. So, you have total entropy change has to be positive. Okay. So, if I want to compute the change in entropy, the change would be delta S, okay, and that change will be nothing but S A E A star minus S A E A plus S B E B star minus S B E B, okay. And I know that this change will be greater than or equal to 0, because I have the change is irreversible. Okay. So, if I write down this delta S, so the right hand side basically means S A E A star minus S A E A is nothing but delta S A over E A into delta E A, okay, plus delta S B and this is greater than or equal to 0, fine. Okay. So, basically what is meant is this quantity is this thing, and this quantity is this term. Okay. So, basically I am writing down the change in entropy as the rate multiplied by the total change in energy. Now, this quantity is nothing but 1 upon T A from the definition of temperature into delta E A, and I have 1 upon T B into delta E B, which is greater than 0. And since delta E A is equal to minus delta E B, that is because E A plus E B is constant, you can rewrite this inequality as 1 upon T A minus 1 upon T B into delta E A greater than or equal to 0. Now, this is the beauty of the second law, that it gives you the direction of heat flow. See, the left hand side is a positive quantity, and that means if you take T B to be greater than T A, so B is hotter than A, okay, that means the quantity in the bracket will be definitely a positive quantity. So, 1 upon T A minus 1 upon T B will be positive, because T B is lesser than T A, so T B is greater than T A. Now, to make the quantity positive, overall quantity positive, I want the delta T A should be also greater than 0. Now, what does this mean? Which means your object A has received a net flow or net flow of energy, which is expected because B was hotter than A. You cannot have a hot body taking a net flow of energy from a cooler body, that is not possible. So, the direction of heat flow is basically decided by the second law of thermodynamics, and that was naturally derived under the constraint of the fact that the entropy of the system has to always increase if the process is irreversible. Okay. So, we had taken the case of a irreversible loss of information, and that has given us the condition that the heat flows from hotter body to a cooler body. So, that ends today's discussion, and the next class we will start with simple examples of in microcanonical ensemble, and we will formalize the various concepts of microcanonical ensemble.